Good morning. Guess it's just you and me, James. All right, no worries. Thanks, James. All right. Just three of us. I'm going to start sharing, and we'll go ahead and get going here. Okay. So we're looking at precipitation today. Precipitation. Whoops. How we determine if precipitation is going to occur. So this is the kind of question you're going to see. Let me go over here. You're going to be asked if the precipitation of something will occur when we have 10.0 mils of something added to, say, 100.0 mils of something else. And you'll notice that these somethings are going to be water soluble. And then when you add them together, you get something that's water insoluble. And whether that thing pops out as a actual precipitate is going to be highly dependent on what the concentrations of the ions actually are in solution. And all of this is related to the Ksp value as we learned about it the other day. So if you've got the MgOH2 example we talked about previously, we know it splits into Mg2 plus and 2OH minus, but it's a solid and it only splits into those ions in very small amounts. Then we can measure the amounts of those ions per calculations we did the other day. And Ksp here is equal to 5.00 times 10 to the negative 11. Now that Ksp value is going to determine which side of the equilibrium we're actually dealing with. So Ksp is going to be Mg2 plus OH minus squared. This is also going to be the Q expression as well. Now remember, the Ksp is what happens at equilibrium. The Q is what happens at any time, including equilibrium, but any time plus equilibrium. So what we know is this. If Q is less than Ksp, then precipitation will not occur. What that implies is that the concentrations here of Mg2 plus and OH minus are too low to reach the Ksp value. So there's too little of each of these in solution to actually get a precipitate to form. That's what it would mean if Q was less than Ksp. If Q is greater than Ksp, then what's going to happen is that the concentrations of these ions would be sufficient to actually cause a precipitate to come out of solution. Does anybody have any questions so far? Now, the way you can think about it, I'll just very briefly go through this because I think it's useful to say this. If we were dealing with, let's say we weren't dealing with Ksp. Let's say we were dealing with the actual just K expression. Get a flat surface here, and I'll try this again. Here we go. So it would still be products over reactants, Mg2 plus and OH minus squared. But I'm trying to bring this back to the way it was when we looked at it back in test 1. And we were talking about Le Chatelier's principle and all of that. Now, we know that the concentration of the solid is something that's meaningless, but I don't want you to focus on that. What I want you to look at is to say, well, look, let's say we've got our Q expression, which is going to be the same thing, right? So it's going to be that same expression. If Q is less than K, then what's going to happen? The top, which is the ions, have to get bigger in order for Q to get closer to K. Does anybody have any questions about that? So I'll write that down. If Q is less than K, top needs to get bigger. And what's on the top? The ions, right? And if the ions are getting bigger, that means precipitation is not occurring. So that's the other way of thinking about it. Now, if Q is less than K, then it's the bottom that needs to get bigger. Sorry, Q is greater than K, I should say, sorry. Let's go back to that. Q is greater than K, then the bottom needs to get bigger. What's on the bottom? The solid. If the solid's getting bigger, what's that mean? It means precipitation is occurring. All right? That's what I'm trying to get at here. Does anybody have any questions? Anybody have any questions about that? Okay, so that's going to form the foundation of what we're going to talk about next. All right, so let's look at the kind of problem you're going to see on the test. So everything above this word answer here is what you get in the question. And that means that you're getting a question about precipitation given adding two different things together in order to get a precipitate. Now, we've all done this before because we've all done experiments where we've added two aqueous solutions together. And here's what I'm talking about, this situation here. So you've got these solutions, they're aqueous. You don't see anything in them except liquid. All right, that's important. And then you add them together. And of course, the volume will be the sum of the volumes here. So let's say volume A and volume B. This will be VA plus VB. So that's part of the issue as well, is that the volumes are changing. And then maybe we'll get a precipitate or not. And by precipitate, I mean, maybe you'll see solid, maybe you won't see solid. That's what we're trying to figure out. And all of this is going to depend upon the concentrations of, in this case, these two ions, the Ca2 plus and the phosphate ion, the PO43 minus ion, in this final solution. So that's what we need. We need the concentration of Ca2 plus and the concentration of PO43 minus in this final solution. Because then what we can do is we can calculate a Q value, which is going to be Ca2 plus cubed phosphate squared. So once we know those concentration values, we can get a Q value, which we can compare to a K value that we're also given. All right, that's the whole point. Now, if this Q value comes out to be less than K, Ksp, no precipitate. If it comes out to be more, then yes, these conditions will form precipitate. That's it. It's really not that. It's really not that complicated. Now, initially, we'll have a concentration of Ca2 plus, which I'm going to call initial, in here. And in the other one, we'll have a concentration of phosphate that's also initial, which is obviously going to be different to the concentrations that we get down here that are final. These are final concentrations. And the calculations we're going to do will first of all entail getting the calcium 2 plus initial concentration and the phosphate initial concentration. And the concentrations we're getting here are going to be in turn determined by how many phosphates there are and how many calciums there are in the initial compounds. That's going to affect things as well. But anyway, that's the very basics of it. Does anybody have any questions so far? All right, let's take a look at the mechanics then of how we do the calculation. Okay. So what you've got to understand here is that in the initial beakers, let's see, so I'll try and make this as, what's that? That's 10.0 mils. Okay, so we have 10.0 mils. This is CaCl2. But we're only interested in the Ca2 plus. The Cl minus is a spectator ion. Now, how do I know what I'm interested in? Well, look at the equation you're given down below that's going to define your precipitate. It's calcium phosphate, so we're only interested in the calcium part of that. The chloride's just going to sit around in solution and do absolutely nothing. We have 100.0 mils of Be3PO42. And again, we're not interested in the beryllium here. We're only interested in the phosphate. So we just want the PO43 minus. That's it. That's all I'm interested in. All right, so let's see what we have to do in order to make this happen. So the first thing we're going to do is get an initial concentration of Ca2 plus. Well, how do we do that? Well, first of all, we have to see how calcium chloride breaks up in solution. So CaCl2, which I'm going to say is aqueous, and that's going to break apart into Ca2 plus and 2 Cl minuses. Remember, we're not interested in the CaCl2 per se, we're interested in this, the Ca2 plus, which is why I've squared it as well. You put a square around it, I should say. Not squared it, put a square around it. So initially, here's what we know, is we're starting out with 6.00 times 10 to the negative 5 molar CaCl2 and we know that the CaCl2 breaks apart to give 1 mole of Ca2 plus for every mole of CaCl2 that we started with. So the calcium 2 plus concentration here, because the moles here will end up cancelling, gives 6.00 times 10 to the negative 5 molar, but that's Ca2 plus. So what have we done there? Well, we found out how much Ca2 plus there was in the CaCl2 solution. This is the initial one, right? So this is initially. The other thing we've got to do is we add all this together, and that's this would be 10.0 mils here. This is 100.0 mils up here. And the volume in here will be 110.0 mils, which is of course the sum of these two up here. So I have to account for the dilution of this calcium 2 plus. And to do that, I use the dilution formula, which is C1V1 equals C2V2, where C1V1 is the concentration that I calculated for the initial calcium 2 plus, times the volume that we initially had of it, which was 10.0 mils. And that equals, well, C2, which is what we're looking for, and V multiplied by the new volume, which is the combination of the two volumes we talked about. This will account for the dilution. So when you calculate this, the concentration of Ca2 plus, which will be the final concentration in that solution, is going to be 5.45 times 10 to the negative 6 molar. And you'll notice that if you look at this number and you compare it to what we started with, it's about 11 times less, which makes sense because we took 10 mils and we put it into 110 mils. So now it's diluted by 11 times, which means the concentration is 11 times less than what it used to be because we've taken that 10 mils and put it in a solution of 110.0 mils. Does anybody have any questions? All right, so that's how we're getting the calcium. I'm going to pull up another window here. Leave that other window behind here for a second. File new. Here we go. So the other thing we're interested in, of course, is what's going on with the phosphate. All right, let me see if I can. Yeah, I'll just put it over here for now. Now the beryllium phosphate splits apart a bit differently than the previous one, but what it does is it breaks apart into 3 Be2 pluses and 2 phosphates. So we have an initial concentration of the beryllium phosphate of 5.00 times 10 to the negative 7 molar. And that's for Be3PO42. But what we're interested in is how much phosphate there is in that specific solution. And it's going to be times 2 moles of phosphate for every 1 mole of Be3PO42. So there's an example of a compound that doesn't have the same initial concentration as the thing we dissolved in the solution in the first place, which was the salt, the beryllium phosphate. So we get 2 phosphates for every 1 mole. We have to take account of that. That came out to be 1.00 times 10 to the negative 6 molar and that's for phosphate, PO43 minus. Now, of course, the other thing we have to do is account for the dilution. And the dilution is what I'm talking about again here, is this situation where we've got the 10.0 mils and 100.0 mils, and we're making a solution that's actually a combination of those 110.0 mils. We have to take account for the fact that we now have 110.0 mils in our volume. The concentration 1 is the concentration I just calculated, 1.00 times 10 to the negative 6 molar PO43 minus times the volume, which we initially have, which is 100.0 mils. And then that equals C2 times 110.0 mils. That's the total volume again. Now the C2 here is going to be 9.09 times 10 to the negative 7, which is just a tad less than what it was actually, because we have taken something that was 100 mils and diluted it to 110. So we haven't really done much to it, but we have done something to it. So that's our phosphate right there. So what do these numbers represent? Okay, so the two numbers I've got down here. So this is again is the final for the phosphate, 9.09 times 10 to the negative 7. Now what these numbers represent here, the 9.09 times 10 to the negative 7 for the phosphate, the 5.45 times 10 to the negative 6 molar for the Ca2 plus, is the concentrations of these guys in this final solution of 110.0 mils. The last thing we need to do here is calculate a Q value, which again we get from the question. Where's the question? Here we go. And the question tells you what we're looking for, and this is how you're going to get your Q. It's going to be Ca2 plus cubed PO43 minus squared. Remember, you're given that equation. You don't have to figure that out. So that's where I'm getting the cubed and the squared from. Now, what values do I put in here? Well, the values I just calculated. 5.45 times 10 to the negative 6. That's cubed. Times 9.09 times 10 to the negative 7. And that's squared. And that comes out with a value of, in this case, 1.33 times 10 to the negative 28. Now this is the value we compared for K value that we've been given, the Ksp value that we've been given. And when I look at the Ksp value, you can see that it would be 1.00 times 10 to the negative 25. So it turns out the value for Q that we calculate is less than the value of Ksp that we're given, which means that no precipitation would occur. So that's what we need to do. Does anybody have any questions? Okay, I'm just going to summarize the steps here and why we're doing what we're doing. But we've got our initial problem here. And in this problem, we're given the initial concentrations of two species. One here is calcium chloride, the other one's beryllium phosphate. it turns out that the calcium and the phosphate will join together to form possibly a precipitate here of calcium phosphate. And we know this because we are given this equation here. So we only have interest here in the calcium and the phosphate. So the first thing we do is we find the concentration of the calcium 2+ in a calcium chloride solution, which in this case happens to be a 1-to-1 mole ratio. So the calcium chloride and the calcium 2+ are going to have the same concentration. We then account for the dilution of taking 10.0 mils and putting it into 110.0 mils. And then that comes out with the final concentration of calcium 2+. We repeat the process with the beryllium phosphate. Knowing now that the phosphate is going to be double the beryllium phosphate concentration because we get 2 phosphates for every 1 beryllium phosphate that we break apart. And then we need to again take that concentration and account for the dilution by using the dilution formula. And that allows us to get a phosphate concentration. We take these two numbers and we put them into the Q expression that we get from the question itself. Is here, Ca2 + cubed, phosphate squared. Come up with a number for Q that we compare to the Ksp value that we're given. If it's more, it's precipitate. If it's less, there's no precipitate. That's it. Does anybody have any questions? Nobody has any questions, huh? All right, let's take a look. Let's take a look at what the test questions look like here for this one. Okay, so the first question, and there's just these two questions that are related to what I just talked about. And this one talks about the relationship between Q and Ksp. And you're going to have to, I'm not going to say anything about that. I want you to figure that one out. I want you to, based on what I had talked about just now, I want you to be able to sort out exactly what that means. All right, what I want to focus on here is the calculation question, which is asking for PQSP. So you're actually not going to be asked if the solution will precipitate or not, because in this case, I'm not giving you a K value to compare it with. What I am asking you to do, though, is to calculate the QSP, which is really the Q value that we're talking about. And it's going to be the PQSP, which means we need to take the negative log of the QSP at the end. Now, the nature of the problem is still the same as what we were just talking about. But but I'm going to go through this specific example here and show you exactly what needs to be done, and you'll see it's going to follow pretty much the same steps as what we just talked about. Okay. Let me shrink that screen a little bit. Okay, there it is. So let's look at what we want first. Well, we're investigating the QSP4. In this case, it's A2D3. Now, don't be too concerned about the charges on any of this, but I know if I have A2D3, if it's a solid, it will split into 2 A's and 3 D's. which is really the important point that I'm trying to get at here. It would be probably A3 minus and D2 plus in reality, but it doesn't really matter what those charges are. What is really important though is to know that if I have A2D3 as a solid, it's going to split up into 2 A's and 3 D's. But I think that's pretty clear. Is anybody uncertain about that? So what are we given though? We're given this A2B3, which is an aqueous solution. But we know that that splits into 2 A3 minus and 3B2 plus. Sorry, 2A3 plus, sorry, and 3B2 minuses. So I should say up here, I'm sorry about that. Let me erase that. If we're talking about regular compounds here, then the cation was always first. I'm sorry about that. There we go. That's better. So the A2B3 splits up into 2 A3s and 3 B2 minuses. But again, don't worry, the charges don't really matter here. Okay, the charges are not that important. All that matters is the sheer numbers of things that we're talking about. So our first step then is to say, well, we've got 240.00 mils of the A2B3, and I need to figure out then what the concentration of the initial concentration of what are we interested in? Well, we're interested in the A, but we're not interested in the B. And the reason for that is because we have A over here in our Q expression. So we're only interested in the A. So to do that, I take the 0.00280. I don't use the 240 yet. I will use it in a bit. 0.00280 molar A2B3 times 2 moles of A, and I'll say it's A3 plus, over 1 mole of A2B3. And unless I'm mistaken, it's 0.00560 molar, and that'll be A3 plus. So you'll notice that because the A2B3 splits into 2 A's, we have double the concentration of A3 plus in the initial solution. And we have to take account of that by doing that equation. The next thing we do is we do the dilution. And this is where we take account of the volumes that we're talking about. 0.00560. Yeah, notice how I'm using this concentration of A3 plus here. Times 240.0 mils. Now I don't have to do any conversions, 0.00 mils. I don't have to do any conversions here of mils into liters or anything because the mils cancel. And the total volume would be the sum of those two, which is 240 plus 390, which would be 630, I believe. So this is going to be the concentration of A3 plus in the final solution. And that's going to be, let's have a look. I get 2.13 times 10 to the negative 3. So what does this represent? Well, it represents the A3 plus in the solution once both solutions have been added together, taking into account two things. That the A2B3 splits into two A3 pluses, and the fact that it gets diluted once we put it into a solution where we're taking two things and putting them together. Does anybody have any questions? Okay. The next part is to handle the C2D5. And what are we interested in? Well, we're interested in the D part here. We're not interested in the C at all. And I know that because what I initially want, which is up here, I want D. Now, C2D5 splits into 2C, and it'll be 2C5 plus most likely, plus 5D, make that clear in there, 5D, and that'll be 2 minus. So I have to take into account the fact that C2D5 breaks into 5D 2 minuses. So let's see, where are we? So it's 0.00375 molar C2D5. And I'm going to get 5 moles of D2 minus for every 1 mole of C2D5. Which comes out to be 0.0188 molar. And that's the D2 minus here. Does anybody have any questions so far? So after that, I need to do the dilution. So C1 V1 equals C2 V2. And the C1 is 0.0188 molarity multiplied by the volume we initially have of that, which is 390.000 mils, sorry, 0.00 mils. And that equals C2 times the total volume, 630.00 mils. And our final concentration of D2 minus is going to be 0.016116. Okay. So what have I found there? Well, I found the final concentrations of both the D2 minus and the A3 plus. That's what I was looking for. And I knew what I was looking for because look at the question. It says, what's the PQSP for A2D3, which means it's the combination of A and D. So I'm only interested in A and D. I'm not interested in B and C. Does anybody have any questions so far? We're not quite done yet. We're almost there. Okay, I'll do this last part on another page here. So we're interested in A2D3, and the Q value there is going to be A3 plus squared D2 minus, whoops. And that's cubed. So we substitute our values that we got in there. We get 0.00213. Squared multiplied by 0.0116. And that's cubed. And then that comes out with the Q value. Let's have a look. And I get 7.08 times 10 to the negative 12. Which looks reasonable, I think. The PQSP is going to be 11.150 is what I get for the PQSP. And that would be the answer I'd plug in at the end there. Does anybody have any questions about any of this? I want to point something out here, and this often leads to confusion for people. You'll notice, let me close this curtain here, it's a little bit bright. There we go. You'll notice that in the thing that we want, we're getting 2 A's. And by coincidence, we get 2 A's out of A2B3. But if you look at what we want again, and we look at the D's, we're getting 3 D's out of that, but we're getting 5 D's out of the initial solution. Now, often people look at that and they see that as being incongruous. They can't, as I said, well, look, how can the initial solution produce 5 and the final solution be 3? And the answer to that lies in what we're doing here. We have the initial solutions, and then we have the final solution. But they're 2 different kettles of fish. So this is C2D5 in here, which of course will lead to 5Ds in the initial solution. And here we've got the A2D3, A2B3, which does give 2 A's. But we're only interested in the precipitation now of A2D3, yeah. Which is different to what we have up here. This is C2D5. So we're looking at 2 different kinds of situations. So it is possible for one solution to be producing different numbers of moles of the element or the anion or cation that we're dealing with in the final solution. It's possible, it could happen, because they're 2 different situations. One's initial, one's final. And that's what you've got to come to terms with. So a very common error that I see here is that because this was 5D down here, people will put this to the 5th up here as well. That's the mistake I'll see. But we know not to make that mistake because of what we want. We want A2D3, not A2D5. Does anybody have any questions? Anybody have any questions? Anybody have any questions? Well, there's only 6 of you here. I don't know if maybe some people will watch this later. Maybe they won't. I don't know. You know, I'm not sure whether to take this as a compliment or an absolute insult. It's hard to know. I can take it as a compliment by saying, well, you know, people feel like they don't have to come to lecture because there's so many resources that they can look at. Or the insult would be that, well, people find me so boring that they don't want to bother coming to lecture. So I'm not really sure which way I'm going with that. Could be a combination of both, I suppose. I don't know. One of those great life mysteries. But I do appreciate you guys being here. Appreciate you making the effort.
Asleep.
What's that?
I think everyone's asleep still.
Yeah, that probably. The thing is, in reality, people do what they want to do at the time, and it's not really a reflection on the person that they're supposed to be doing something with at that time, that they're doing something else.
I almost didn't wake up today.
That's the reality of it. All right. Does anybody have any questions? Anything at all? All right. Well, you know, to the people who are here, I will say this. For this particular test, there's a fair amount of material to go through. It's not really something that you can. One of my friends relies on your resources. So thanks, Jack. So one of the things about this is that you cannot leave this until the day of the test to start looking at it. There's just too much stuff here. So what we know is this. Let's look at the timelines here. So I'm just going to pull up the syllabus here. Make sure everybody's aware of what's going on. This is I think this is one of the harder tests. And it's not that the material's that hard, it's just there's a lot of it. There's a lot of it, you know, there's a lot of stuff here. And the thing is, you have to go through, you have to understand everything. It's not like you can memorize stuff. You have to understand it. And that's really the kicker here. All right, let's have a look. Syllabus. So today, this is October 1st, when we were just finishing up with the precipitation here. On Tuesday, there will be a review day, right? So I'm going to spend some time today reviewing. So I'll start review today, but I'll finish review on Tuesday. The test is going to be on Thursday, or due on Thursday. That's not to say you have to wait till Thursday to take it. You can take it any time before that. It's due. It's available now if people want to take it now, and that's fine. The extra credit, the fun quizzes, they're all due on Wednesday at 11:59 p.m. And I'm just trying to think. Don't think I've got any. Yeah, that's right. Yeah, so it's just that. Yeah, so the extra credit is all due on, yeah, we'll just say that. The extra credit's all due on Wednesday, 11:59 p.m. So make sure you get all that handled by then. And then the test would be due the following day. But again, make sure you get it done as quickly as you can. All right, does anybody have any questions about timelines here? So you got a week, right? We've done all the material now. You've got a week. There's no excuses. People can't say, oh, look, I don't like studying until we've done everything. Okay, we've done everything. Now you can start studying, all right? So nobody can come back to me and say, oh, you know, we didn't have enough time, right? No. I'd still argue you can still start studying even before you finished all the material by studying the material we've already done. I still say that people should be doing that. I know that's not the reality, but you know, that's what I think should happen. Okay, So let's look at, we'll start at the beginning here and we'll look at the test. Now remember that for test 2, it's going to be exactly the same as the ungraded copy, exactly the same, same formatting, everything else. I do have videos for every single type of problem and every possibility for those types of problems. So I wasn't lazy about this. I did give you every single possibility here. So for 10 to 11, there's actually 4 possibilities that you can get. And I have got videos for all 4 possibilities, even though you're not going to get all 4, you're only going to get 2 of them. So 16 to 17, same deal. So for any of those that you see when you're going through and taking this, that's what's going to happen. The periodic table and everything will be given to you inside the test, so you don't need a copy of that, just like it is in the ungraded copy. All right, any other questions so far, just about anything general here about the test? Okay, so I am going to go through an example of one of these, so we'll see how it goes. So starting here at the first grouping of questions, which is question 1, where we're looking at titration curves. And the first question here, it says strong acid titrated with weak base. So let's go through how we might look at that first. So what I would do is I wouldn't be looking at the answers yet. I wouldn't look at any of the answers, to be honest. I think they might try and mislead me. So what I would do is I'd just try and come up with the titration curve first and then match it at the end. So let's have pH, and then we'll have, in this case, we're titrating strong acid with weak base. So the volume of weak base goes down here on the bottom. We're starting with the strong acid, which means the pH, the starting pH will be 1. The final pH will be the pH of the weak base, which is going to be a pH of 9. So I know that my general curve is going to look like that. And then we're starting at 1 and going up to 9. And the next thing we would do then is try and determine if we're going to have a buffer region or not. Now we can only have a buffer region if we're adding strong acid or strong base down here. So there would be no buffer. So I would look for the one that looked like the one I just drew. We're starting at 1, going to 9, but with no buffer region. And then I would hunt down that. So it wouldn't be that one because that one has a buffer region. A lot of answers here. And there it is. That would be the answer I'd pick. Does anybody have any questions? Okay. So what are the products of this reaction? And we've got CH3Li, which I'm telling you is a strong base, and LiHCO3, which is a weak acid. The clues I'm using here, I know that this is the weak acid, so I know it's producing H+. And the CH3Li, I would split into CH3- and Li+. The metal ion always taking on the positive charge and everything else taking on the negative charge. So if this is coming up as H+, then the rest of it would be LiCO3 negative. That's all I've done is I've just taken out the H plus and seen what I've got left at the end. So the CH3 minus will join with the H plus, the Li plus will join with the LiCO3 minus, and I'll end up with CH4 plus Li2CO3. So that would be my final answer. Does anybody have any questions? Anybody have any questions? Okay. Question 3, which indicator is the best to use for the following titration? We have a strong base. It says strong base with weak acid, which actually happens to match what I've got up there. But if we've got strong base and weak acid, that means that, well, actually, no, it's not the same as that one. It means that we're dealing with a situation where we're starting with a strong base, which is 14, and we're going down to 5. So we're looking at the average of those, which would be 9, which is where the equivalence point would be. And then I choose the one that lies within where the equivalence point lies, and that would be phenolphthalein for that one. Anybody got any questions for number 3? So you are given a periodic table to be in the same place in the test you're taking. Remember, if you can't see something or you need a number or something, you can always do, I don't think you'll need a number at all here because you never need any of these small masses. But if you did need them, you could always do Command or Control plus on your keyboard. That will enlarge the screen and enlarge that diagram as well. Then Command minus will bring it back, but you don't really need it. So I don't think it's anything to be really concerned about, to be honest. But anyways. So let's see. So looking at acidity here. So which compound is more acidic? And the one that's more acidic will be the one that has the more stable anion. So often what I like to do is sort of remove any doubt and actually draw out what the anions look like. So for the first one, the anion will look like with the O negative and the H plus off to the side. And then we've got the other one, which will be with the Cl on it. And then I would ask myself, well, which one of these anions is more stable? What I know about this is that's going to be delta minus, and that's going to be delta plus. And that delta plus will enable a bit more stabilization of the O negative. So I know that this anion here is going to be the more stable of the two, which makes the bottom compound here more acidic. So that's the kind of thought process I want you to go through. Which compound has the least stable anion? Well, this one's kind of similar. So I'm just going to shortcut this a little bit. That's one anion, and here's the other anion. And we've got delta minus on the Cl, delta plus on the C. So the delta plus on the C, in the one that has the Cl, will enable some stabilization, whereas the bottom one doesn't have anything to stabilize the O negative like the top one does. So this one is the one that would be the less stable of the two anions. Does anybody have any questions? Okay, the reason one of these anions is more stable than the other, so you look at it, you can see that we've got Cl and Cl, so and they're in different locations. So we know it's got to be something to do with distance from the negative charge. And that's why this one I would be talking about something closer. So that would be the answer there. So what I would ask you to do is go back through the lectures that I talked about where I mentioned those 4 scenarios, those 4 different scenarios, and how to tell the difference between them. And that will certainly help you with that question. And in this last part here, what's the correct statement that links acidity to anion stability? Well, it's always going to be the same kind of statement. But what it's about is comparing the stability of the anions to the acidities of the initial compounds. So usually it starts out with the anion of one being more stable than the anion of the other, meaning that the initial compound is more acidic than the other compound. And that's going to be the basis of it. But again, I'm going to ask you to go through that, go back to the lectures and figure that out. There's a lot of answers there, so you have to make sure your wording is correct. A lot of people don't like these kinds of questions because you actually have to figure it out, but that's the thing. I want you to figure it out. I want you to, that's why I put lots of answers in there, so you just can't guess. You know, you actually got to know what you're doing. Go figure, huh? Okay, so calculation of Ka and Kb. So this is one for which I think you can have a number of possibilities. It all depends on what you're given, whether you're given POH or pH for something like this. But let's take a look at number 8. So it's Ka we're looking for, which means that we know what we need to do with this XH. XH is going to need to be split into X minus and H plus. The key here is being the A. The A tells us it's acid. And that leads us to knowing that we're getting H plus here as part of it. So the initial molarity here is going to be 0.26 molar. 0 and 0 equilibrium. It's going to be 0.26 minus Z and Z and Z. So we're told here we have the pH of 1.2. So it turns out we need H plus. So we've got pH, which means I don't have to subtract from 14 to get anything. So the pH is 1.2, which means the concentration of H plus is going to be 10 to the negative 1.2, 10 to the negative pH, 10 to the negative 1.2. And I get 0.063 for that one. For the concentration of H plus, which happens to equal the value of Z. So the Ka is going to be X minus H plus over XH. Which is Z squared over 0.26 minus Z. Now I plug all that in, and it's going to be 0.063 squared over 0.26 minus 0.063. And what you want to do there is do the addition part, or subtraction I should say, separately, and then come out with your Ka value. And for that one, I get 0.0198 or 0.020. Whoops. But the key part of that one is understanding what to do if you've got pH or pOH in your question. Does anybody have any questions about that one?
You don't have to take the negative log of that one?
No, because you're not asked for the pKa, you're asked for the Ka.
Okay, just the Ka. Okay.
Yeah. Yeah, if it was pKa, yeah, that's what you'd have to do. Just look at the question and you'll know. But generally, the answers to these come out with no more than 4 zeros at the front. So I don't really see that as being too bad to sort of plug in as the answer. Otherwise, I probably would have asked for pKa or pKb. So the next one, we got Kb. And B is for base, of course, which means that I take the compound, which is X, plus, actually I'll do it the other way around, make it a little bit easier. So H2O plus X, and that'll give XH plus OH minus as a product. And then we'll have our initial. And our equilibrium. The X is 0.39, 0 and 0, and then 0.39 minus Z and Z and Z. We're given here the pH. So what I'm going to need to do is figure out the pOH. Now, why do I know I need that? I know that because it was Kb and base gives OH minus here as a product. So that means that I'm going to need the pOH, which is why I'm going to have to take the pH and subtract it from 14. So the pOH is going to equal 14 minus the pH. And that's, let's see, 1.2, that'd be 12.8. Sorry, 12.9 is 1.1. All right, there we go. I'll do this out properly. 14 minus 12.9. So it's 1.1. Now from there I can get the concentration of OH minus, which is going to be 10 to the negative pOH, which is 10 to the negative 1.1. And I get 0.079 for that. And we do the same thing as we did previously. So the Kb is going to equal the XH plus OH minus over the X which is going to be Z squared over 0.39 minus Z. And that would be 0.079 squared over 0.39 minus 0.079. So as we did before, we'll have 0.079 squared over the subtraction there, which would be, in this case, 0.31. And then that gives us our final answer. All right, does anybody have any questions? So that's probably a good place to leave it, and we'll continue with the fun on Tuesday. All right, so it's going to be just a review day. So if anybody's got, so start working on this, and if you have any questions, you can always ask me then as well. All right, anybody got any other final questions here? Oh, okay, no worries. Yes, you're welcome. Okay, well, I'll see you all later.
Thank you.
Bye.
Bye.